I once again welcome you all of you the lecture series of microcontrollers and microprocessor. So now see this. Now we are in day 14. The date is 8/5/2020. Okay. Now we are entering the second unit or second chapter called as minimum and maximum mode operations of 8086 microprocessor. You know that very well. So microprocessor can operate in two different modes, minimum mode, or you can also call it as a single mode, maximum mode. You can also call it as a multiple mode. So for that modes, how the microprocessor is operated. Okay, how our 8086 microprocessor is operated. Okay, so what is the difference between the minimum mode to the maximum mode? So what type of pins are available for minimum mode to the maximum mode? You know that our 8086 microprocessor is a 40 pin microprocessor. Okay, out of that 40 pins, so 32 pins are common for both the maximum and the minimum mode. Only 8 pins are different from the maximum to the minimum mode. So how you can utilize that pins in different modes of the microprocessor. You know that for changing the one mode to the another mode, we have one pin is there mn/mx bar. Okay, so that pin is available to change the maximum mode to the minimum mode or minimum mode to the maximum mode and all. Okay, so now see this in the second chapter, the syllabus is like this. The instruction set. You know that a set of instructions is called a program. Okay, instruction set. What are the different types of instruction set? How to syntax? Nothing but syntax of the each and every command and all the things will learn from this instruction set. For suppose like move ax comma bx. For suppose I write this one. So this is the instruction set. This we can call it as a mnemonic. Mnemonic. These are the operands. Then another type of instructions are the move ax comma some data or slash some address. Different types of instruction sets are there. So how to write this instruction set and all we will see it in the instruction set as well as addressing. Then you know that minimum and maximum modes of 8086 microprocessor and all how the microprocessor is perform in minimum mode as well as how the microprocessor is perform in maximum mode. How to draw the read and write cycles of the minimum and maximum mode. We will see it. Okay. So once again, we'll go for the again you can see the some microprocessor diagram. This is the CPU. By that CPU, we are able to connect the memory and the input-output devices through these buses. So address bus, general. You know that there's some general bus operations. On that one, we have the address bus, data bus. At the same time, control bus. We have the okay. So you have different types of buses are available. So by synchronizing input and output devices, we are using some interfacing devices. And by synchronizing this input out, we have uses some latches, trans receivers to convert for suppose a bus is consider the address lines 80 to the 8015. You know that these are in both address lines as well as data lines. Whenever you want to convert some address to the data lines, we are enabling ALE, address latches enable latch. So we are using latches, address latch enable latches. So the hardware device latches are available. So at the same time, trans receivers are available. Some D type of the flip flops are available. So to synchronize this memory and input-output devices. Okay. Okay, so now in the last class we are already seen the general bus operation of the 8086 microprocessor. Nothing but memory read cycle and memory write cycle. Memory read and memory write cycle. Okay, we'll see it in So you know that. So for read cycle, microprocessor is required four cycles. At the same time, for write cycles also microprocessor is required four cycles. Okay. So nothing but TW is a wait period to synchronize the to match the speed of the slower memory device as well as the CPU. We are using this TW. Yeah, same. So this TW can also call it as a wait period or inactive period. You can also call it as. So for performing memory read operations and the write operations, so microprocessor is generate for clock cycles. Okay, so you know that what is ALE, address latch enable, then address to the data, then address to the status lines, address to the data, read and interrupt lines, ready lines. You know that for synchronizing slow memory devices, we are using this ready data transmit and data receive lines, data enable lines, and write lines. Okay, so last class we are very much discussed on the this general bus operation. Now, today we are also going to discuss the minimum and maximum timing diagrams also if possible. Okay. So today we are going to discuss the minimum mode. Then next class we will see it in the maximum mode operations. So now see this minimum mode operation of 8086 microprocessor. Then control signal interfacing. Then a very simple diagram. I don't just we are using some DMUXs for this one control signal interface. We are using some DMUX. DMUX we are using some DMUXs and all. So then timing diagrams of read and write cycles. These are very much similar to the general bus operation of the 8086 microprocessor diagrams. Okay. Now see this minimum mode. You know that how this microprocessor is convert one mode to the another mode. Yes, see this. This MN slash mx bar is equal to the 1. You know that this mn is a minimum, mx is maximum. You know that whenever there is any logic, any pin that represents a bar, it works as 0. Nothing but 0 is on, 1 is off. But whenever you want to operate our microprocessor is minimum mode, that's why mn is equal to the 1 because it is not the bar. So that's why is equal to the 1, it works as a minimum mode. So it is equal to the 0, it works as a maximum mode. You know that microprocessor is always in one state, that is the minimum mode. Okay. So for so our intention is to operate microprocessor 8086. So that purpose, microprocessor have some one pin. That pin you can call it as mn slash mx bar. If that pin is equal to the one, microprocessor work as a minimum mode. Otherwise, it will work as a maximum mode. Otherwise means it 0. Okay, so whenever you are interfacing this CPU as well as this memory devices, memory device and input output device, you know that we have some interfacing devices means 8255 PPI. Okay, 8255 PPI devices. Some you require some 8279 keyboard and LCD keyboard and display devices. Some DMA controllers, some USART controllers. The type of controllers are needed to connect the input-output devices as well as memory to the CPU at the same time. So, at the same time, whenever you want to interface in this memory input output devices, so you require interfacing devices. At the same time you require some latches as well as some transceivers, some input output devices, and all. So now we can see this. So whenever you want to interface, so you know that minimum mode of operation, you can also call it as a single processor mode. Single processor mode. Single processor mode. You can also call it as a single processor mode. See this single processor mode. So by interfacing this by interfacing this microprocessor to the memory devices, we require some latches. See this latches, transducers, clocks, and radars. A clock is common for any mode of the operation. The clock we have the available in So three different categories. You know that what are the three different category of clocks available in 8086 microprocessor? At the moment, 5 megahertz clocks are available. At the same time, 8 megahertz and 10 megahertz clocks are also available. Then memory and IO device. Simple. You cannot confuse that one. You know that this is the pin diagram, a 40 pins pin diagram for suppose. So this is a minimum mode. This is the some maximum mode. You know that some pins, only 8 pins are different for this one. So for this diagram, for this microprocessor CPU, for suppose CPU, we are going to connect the memory or input output devices. Okay, you require some this type of devices, latches, receivers, clocks, generators, okay, and all. Okay, now we can see this each and every what is latch. So why we are using latches means here. So microprocessor, why this, especially why this type of latches, receivers are needed for this 8086 microprocessor is. So whenever you are using the microprocessor 8086 as a party pin microprocessor. So this party pins we are using as a for some pins we are using it as a multi-purpose pins. At the same time, some pins we can use it as a bi-directional pins also. Remembered why we require latches, receivers, and all. That means so our 8086 microprocessor is a 40 pin microprocessor for better utility of the 40 pins. For some pins we are using for multi-purpose for or nothing but multiplex modes for suppose these are a best example for this one. I mean, so whatever for suppose AD0 to the AD15 one example. So the same pins will work as address, at the same pins will work as a data link. So whenever microprocessor is always in one state, we can call it as a address state. This was address node. This microprocessor. Whenever we want to convert this address to the data, so we are enable the address latches enable. So nothing but these are the hardware devices. So these are the only triggering pulse to apply for the device to on the device to convert one state to the another state. The stating, the change of state is nothing but the flip flops. Simply a flip flops we are using, but change the one state to the another state. This ALE is it work as some trigger. So you know the clock, this clock ALE, you know the D flip flops. So D flip flop. So 74LS something flip flops also are used for this latches at the same time transistors. Now we can see this each and every one. You know that I think you understand why you require latches, transistors, and all. Okay, why this transistors means, so this data process will carry the data, so for that one, for that purpose, how do so how this device will carry the data and will see it in the transistors. Okay, you see this latches is nothing but a D type flip flops like 74LS, 373 or 828. You know that the D flip flop, a clock here we are using in this clock, and ALE. Okay, remember ALE here. You can enable that one. Enable whenever you want to enable any flip flop. We are giving some clocks. So ALE instead of clock, you can represent the ALE. D, you know the D. So one is of D and D bar for suppose D bar. So one is that one. You know the diagram very well. So so now this clock we are using as ALE signal. Okay, so our microprocessor is using AD address 20 bus address. AD0 to the AD15 is nothing but the A0 to the A15 addresses, and what are the addresses? Remain A16 to the A19. Total we have 20 bus address. 20 bus address. We have 20 bus address. We have 20 bus address. Okay, 20 bus address we have. So for that purpose, so address is 20 address lines. but data is D0 to the D15. D0 to the data lines are D0 to the D15. D0 to the uh, D15 is nothing but the only 16 data lines. 16 data lines. So now see, this address is 20, but the data is only of 16 data lines. For enabling this one, so we require the some latches. Nothing but we can convert this address mode to the data mode for this flip flops. Nothing but the latch is like a flip flop. To convert one mode to the another mode is process. So we require this one. So for this 20 bits, this is the important point series. So for this 20 address lines as well as 16 data lines of the CPU requires 8086 microprocessor requires 3 octal address latches and 2 octal data buffers for completing the address and data separation. Remember to convert some address lines to the data bus and all, microprocessor, nothing but the CPU requires 3 octal address latches. Octal means here 8. Remember, octal means here 8. Okay, so 3 means 3 into 8 output addresses, and we require the and 2 octal data buffers, 2 octal data buffers, 2 octal 8 into 2 only. Okay, 8 into 2 only, so 16 is sufficient. So you know that so this latches so that are available at 4 bit or you know that 4 bit or 8 bit or 16 bit or and so on. It is multiple of 2 latches are available, but these flip flops are available multiple of 2, 4 bit or 8 bit or 16 bit and so on. So for address purpose, so it required the 8 latches. I mean after nothing but 3 8-bit latches, 3 8-bit latches. You know that number of 4-bit latches, 8-bit latches, 16-bit latches, and all. So for that, for address buses, we require the 3 8-bit latches. For data buses, it require the 2 8-bit latches because these are the 16 bits only. This address line is a 16-bit address line. So this this data line is a 16-bit data line, but the address is a 20-bit data line. So 20, that's why 24. 3 is a 20. So that's why. So it is not exactly 20 because these are available in octal. So that's why some 4 bits are inactive state. So only 20 bits are okay. Okay. Now see this. These are the latches diagrams. You know that SAM for LS for data purpose, for address purpose. You know that. So you know that for address purpose, for address, it requires the 3 into 8 octal, 3 into 8 bits. So nothing but 24 bits. So now see this. This is one 8-bit processor. This is one 8-bit processor. This is one 8-bit processor. Nothing but 8-bit octal lines. Now see this. How we can divide this one? Addresses are divided. You see this 0 to 7. They divided into A0 to the A7 is divided by the one latch. So 8 bits. Now see this. These are the 8 bits. So nothing but we will draw the like this only. Yes, see this. Second, I will erase this one. We'll see this. We will A0. We can also write it as A1 is like this, A2, and so on. A7. This is the one latch. Then what is the second latch here? A8. A9 is the second latch, A10 and so on. A15 is the second latch. You know this address is 20 bus. So here this one is A16, then A17, okay, A17 and so on, A19. So these are the 20-bit address. What about the remaining 4 bits? These are inactive state. So you don't. So you need not to worry that one. So we'll connect how these latches will be connected by these lines. You know this 8086. You remember the pin diagram of this processor. You have the some pins like AD0 to the AD15, AD15. Then A16 S slash to the A19 slash S7. You know that some pins. You see this, you see these pins. AD0 to 7, AD8 to the AD15, then A16 to the, you know that S3, S6 and so on will represent as the status lines. You know that. So this, how this status, so these are the pin microprocessor, our 8086 microprocessor. These are the, you just, in our mind, you just remember that what are the pins of that microprocessor, 8086 microprocessor pins, 40 pins microprocessor. In this side, we have some AD0 to the 59s. In this side, we have A8, A16 to the A99s. So all that 20 pins are connected by these three latches. So in this way, for diagram, it represents, for the simplicity purpose, diagram is represent like this. Now see this, the data lines, nothing but the pins that are connected to this latches. At the same time, for the same time, to carry the data lines, to carry the data. For that purpose, require the only two latches, two 8-bit latches. This is 8-bit latch. At the same time, this is also 8-bit latch. Okay, two 8-bit latches. Okay, so because D0 to 7, but 8 bits, again here 8 bits. So two latches are sufficient, but here 8, 8 and 8, 24. Okay. So now see this, these are the latches we are using for, these are, yeah, these are latches, 374 LS373 model latches we are using for address. At the same time, 245 latches we are using for the data purposes. You know that pins, you see these pins for data purpose. Whenever you want to talk the data, so you require the dt by r or den bar. For this enabling, for this one to carry this one, you require the trans receivers. For that purpose, we require the trans receivers. For address to the data conversions and all, we require the latches. For whatever, what about the data? Whenever you have to take the data, you receive the data, transmit the data, you can enable the data, and all, you require the trans receivers. Okay, these are the purpose. Okay, now see this. These are the some decoders while we are connecting the diagram. So the syllabus also, they represents the control signals of 8086 microprocessor. This may be they asked the for a question. Okay, you should remember this one. So very easy. So this is the basic diagram, inbuilt this one. So this is the 3:8 decoder. So in this decoder, the internal part is like this. Internally, the decoder is like this. This is the 3:8 decoder, 3 to 8 decoder. It's simply called as a 3 to 8 decoder. So the internal part is like this. You know that what is the input of this one? Input of this one, a read WR bar symbol, a WR bar pin, RD bar pin. You know that this we have the pin diagram, pins, microprocessor 8086 microprocessor were connected by this decoder. You know that how you know, you want to see this, you want to understand. So just microprocessor, you know that you just remember the pin diagram, that the structure of the microprocessor, the image of that microprocessor. It has only 40 pin microprocessor. For working for this microprocessor, to interface that microprocessor to the memory and input output device, you require this type of devices, more number of devices, latches, trans receivers, decoder circuits, then the control logic circuits. These are the control logic circuits, and as well as the some interfacing devices, 8255 PPA devices. So many number of devices are required to interface this memory and as well as input output devices. Okay, so this is one type. So this by this pins, WR bar, RD bar, M by IO bar pins. So they are connected and external. These are all are available in external. Remember, these are all are available in the external, not in microprocessor. These are all are available. So this is the CPU. In the CPU, you know that this is the pins. So this CPU has the pins only. Remember, pins only. This whatever you are discussing, interface devices, latches, trans receivers, and this decoders, multiplexes, so all are available in the outer side of the chip. All are available at the outer side of the chip. Remember, this is the chip. Okay. Okay, see this internal part. So the decoder. So WR bar pin, we are connected this decoder pin. RD bar pin is connected to the B pin. M by IO bar pin is connected to the A. Nothing but yeah, most significant bit as well as the least significant bit. So this bit will convert to the this part. This is and decoder inbuilt is like this. This is uh, nothing but a gate. We are using this type of NAND gates and all. We will see this. So out of these 3 pins, we are converting to the 6 pins. I mean 4 pins and all. 4 pins and we can see this. So what is MWR? What is this MWR? What is this MRD bar? What is this IOWR bar? IORD bar. You know that. You again once again come back to this microprocessor diagram. You know that microprocessor is connected both memory as well as the input output device. Okay, microprocessor is connected memory as well as the input output devices. You want to tell that microprocessor, you want to connect the memory or you want to connect the input output device. You want to tell that microprocessor. You given the information to the CPU to connect the memory. So you given the information to the CPU to connect the memory, or you given the information to the CPU to connect the input output devices. How you can given that information to this uh, CPU to connect the memory and input device? You have the one pin M by IO bar. M by IO bar pin is available. You know that one pin. What is that pin? M by IO bar pin is available. M by IO bar. If it is equal to the 1, it is connected to the memory. Otherwise, it is equal to 0, it is connected to the input output devices. Then, so this pin is available to convert some. So, for suppose microprocessor is connected to the memory, you want to enable that pin. Okay, you want to enable that pin. So that is connected to the input output devices and all. For suppose, then how to know that microprocessor? If pin is available, you okay? That is very well. Okay, very well. So microprocessor has the 2 pins. So IO by M bar pin to transfer the some memory state to the input output devices. Okay, very well. Okay, very well. That pin is available. Why that pin? Hardware pin is available. Why that hardware pin is available? To change the memory to the input output state. But you are not manually pressing any 0 or 1 to that pin, or you are not manually given to that uh, any instruction to that CPU. Then how to work with CPU? How you can given some commands to that CPU? Or you simply write this some programming? Remember, you simply write the programming only. You are not at all pressing any pin numbers. You are not at all putting zeros and ones and outs by using some outer side devices and all. You just write the some programming to enable or disable the pin and all. Okay, so for this one, how to know that for this one? So if it is connected to the input output device and memory, remember. So you know that microprocessor, it work as zeros or one. Pins also work as zeros or one. So if it is microprocessor is always at one state, it is always either 0 or 1. So microprocessor is always connected to the memory. Or whenever you want to connect this memory to the input output device, you simply put the IO bar is equal to 0. Okay, that's it. But how to put that one? How to know that microprocessor? How to given some command? You given some commands, simply in and out commands. In and out commands. In is input device, out is output device. So then microprocessors know that. So you gather the information from that input output devices. Then microprocessor changes this one state to the 0 state. So by changing the states and all, so see this IO by M bar pin. So you see this IO by M bar pin. You change this state IO by, if it is 1, microprocessor change the state to the 0. For suppose, you know that 1 0, what will happen to that NAND gate? So the entire output of that microprocessor is changes. So that is the way. So WR by 0, it is 0. If it is always is 1, you want that for suppose you write the in and out instruction, it changes to the state 0 0 0 0. decoder input, or 001 decoder input. You know that how the output is changes. How that output is changes is simply of gate. You know that the gate to truth table. You know that 001 101. If it is input is changes, this output is also changed. Okay, this is the way microprocessor is changing the one state to the another state. Some memory to the input output devices, add some address lines to the data lines. Okay, so what are the trans receivers? You know that why we require the trans receivers. You know that trans receivers, you know that we will see this diagram. Data enable lines, DEN means data enable, and what is DT? DT by R bar means data transmit and data receive purpose. So we require the trans receivers. So because why we require these trans receivers once again means here. So you know that our pins, our buses, some buses are bi-directional, but we can both sides. We can send the information by using same lines, at the same time can receive the information by using the same lines. The best example is D0 to the D15 lines. Data bus D0 to the D15 lines. We can send the information from the microprocessor to the CPU, another but microprocessor to the memory, or CPU to the memory. At the same time, you receive the information from memory to the CPU. So bi-directional buffers are available to transmit that same pins are for one state to the another state, for nothing but the forward state as well as the reverse state, something like that. For that purpose, we require some controllers, namely DEN DT by R bar. What is DEN? Data enable. DEN bar is equal to 0 means here it works as a 0. So work as a 0. So why we are required this DEN bar means here. So this it indicates that the valid data is available on the data bus. It indicates that the valid data is available on the data bus. So valid data is available on the data bus. It indicates that way. So what is DTP R bar means here? If it is equal to 1, data transmit. If it is equal to 0, receive. So nothing but transmit means here CPU to the memory. Receive means here memory to the CPU. Okay. So DTP R bar means here direction of the data from the processor to the memory, or memory to the processor. So then you know that clock. What is the clock? Like an external clock, you are supplying the quad crystal oscillator clock. But a 5 megahertz clock. We have the 8 megahertz clock. Then we have the 10 megahertz clock. This clock is also not available in the CPU. Remember, as I said. So as I said, this clock is supplied by the quartz crystal oscillator. Quartz crystal oscillator that will given by the outer side of the microprocessor. Okay. So now see this. This is the diagram of minimum mode system. Now this is our CPU. Now this is our CPU. So this is the memory you are. This is the memory you want to connect this one. This is the memory you want to connect this one. See this. For our diagram, you simply draw this one. CPU. So is connected to the either memory. See this. Either memory. Simply see this. Or input output device. But the CPU is connected to the memory. You want this much of devices in between this. See this. How many? Nearly of 3 different types of hardware devices are used to connect the CPU to the memory. In between, yes, in between this we have this such type of hardware device. A DMux, you know that what is the DMux? We are already see 3:8 DMux. What is the input of this DMux? Read pin, write pin, IO by M bar pin. So this will indicates the yes, you know that this will indicates the M by RD bar means memory read, WR means memory write, IO RD bar means input output read, IOWR means input output write. So input output read, input output write. So because the same data lines are used for both memory as well as input output devices. For that purpose, we are using this DMUX. DMUX. You know that this latches. You know that we have five different types of latches are there. Five different types of latches. Five different means here for data purpose you require the two 8-bit latches. For address purpose you require the three different 8-bit bit latches. No series. Three different 8-bit latches. So this DMUX is used to connect the memory and the input output devices. But it will separate the whether the CPU is connected to the memory device or the CPU is connected to the input output device. So these latches are going to helpful for converting the address to the data buses. Then what is this control logic? So this is new to you. What is this control logic? Control logic means you know that this memory is RAM and ROM. You know that what is memory? A part is divided by the RAM, another A part is divided by the ROM. A part is divided by the RAM, another A part is divided by the ROM. Okay, so for this purpose, then CPU is want to connect either RAM or ROM. Which device? Which type is either RAM or ROM memory? RAM memory and CPU may get access to the RAM memory or ROM memory. How to know that one? That will given by the bus I enable pin. Bus I enable. Bus I enable. Remember that will be connected by the bus I enable pin. That will help to bus I enable as well as A0 pin. There is a one truth table for this one BHE and A0 bar. You want to see this. So now see this. If this control logic is CSC bar is represents the RAM and ROM, you see this whether this it's connected to the RAM at the same time. It will help to connect the RAM at the same time. It will help to connect the ROM. Okay, this is the RAM memory. This is the ROM memory. This is the input output device. Very simple this one. So CPU memory and input output devices for connecting this one, you want to know that this type of devices are required. DMUXs. Okay, CS means a chip selection. Remember, chip selection logic. CS means remember. CS means chip selection logic. Chip selection logic. And you know that this trans receivers and latches. You know that how many latches we require? We require how many latches? We require eight different latches we require. Okay, then you require some trans receivers to connect the CPU to the input output devices. So this is a minimum mode diagram. Similarly, maximum mode is also almost all same. Okay, this is our CPU. This is our CPU. You know that for the CPUs, this is the clock. A quartz crystal oscillator. This is the clock. A clock is supplied by the outer side of the device. This is the clock. Quartz crystal oscillator. So now see this some timing diagrams and all. You know that minimum mode timing diagrams is very much quite similar to the general bus operation of the microprocessor. You know that what is timing diagram? What is the timing diagram? Timing diagram is graphical representation of the operation of microprocessor with respect to the time. A timing diagram is knows the operation of the microprocessor. Nothing but it will graphically you want to show the microprocessor is performing read operation and microprocessor how that microprocessor is perform read operation or how that microprocessor is perform write operation and all by showing graphically you can call it as a timing diagrams. So now you can remember this one. You are frequently using this now. A state and a mission cycle and the instruction cycle and all. So one mission cycle is nothing but for read operation microprocessors perform the 4 clock cycles. You can call it as one mission cycle. Okay, for suppose then some different mission cycles are used to perform the one instruction cycle also. So that are based on the instructions, the type of instruction you are giving. Some, for suppose addition instruction you are giving, multiple multiplication instruction you are giving, or interrupt instruction you are giving, or input instruction you are giving, or output instruction you are giving, or move instruction you are giving, or stack instruction you are giving, or push instruction or pull instruction you are giving. That instruction cycle is entirely based on the instruction type of instruction you are giving. What is the state represent? One cycle of the clock we can call it as a state. One cycle of the clock. Then what is mission cycle? What is a mission cycle? For suppose microprocessor operates such a read for write operation, or some microprocessors perform some read operation or write operation, memory read or memory write operation. So it can require a specific number of cycles. A specific number. For read cycle, you require the 4 states of the clocks. For write cycle, require the 4 states of the clock. That you can call it as a one mission cycle. One mission cycle. One mission cycle. 4. Now see this. For suppose this. This is the one mission cycle. You know that this is the one mission cycle. This is the first 4 states. State 1, state 2, state 3, state 4. These are the states. You can simply call it as a time period 1, time period 2, time period 3, time period 4. This we can call it as states. So for completing this instruction, it required 4 states. We can call it as one mission cycle. Or a group of instruction mission cycles are required to see this. A time required for microprocessor to fetch and execute an entire instruction is called instruction cycle. For performing this instruction cycle, microprocessors need to perform the more than one mission cycle. So it's very simple. Instruction cycle is nothing but time required to microprocessor time required for microprocessor to fetch and execute an entire instruction is called the instruction cycle. You know that microprocessor for architecture divided into the bus interface unit as well as the execution unit. What is the execution unit functionality? To fetch that instruction, at the same time to decode that instruction. So for that purpose, it requires some more number of mission cycles. But you are only seeing the read and write cycles only. But there are some operations is like it will take the 19 to 20 states of that cycles only. Cycles some operations are there. It will take 19 to 20 states, and nothing but 4 to 5 mission cycles are required to perform the one instruction cycle. Instruction for suppose move for suppose ax comma bx, ax comma bx. So the number of cycles to require the microprocessor to fetch the information, fetching, to decode that one is called the instruction cycle. A fetching means here where the data is available. The data is available at the memory. For fetching that one, microprocessor perform the read operation. It requires the four states are one mission cycle. Then how to execute this instruction? This is by executing this instruction, microprocessor is again some generating some another mission cycle. So all these are commonly known as the instructions. Okay, all these based on the instruction cycle. Okay, now see this. This minimum mode and maximum mode timing diagrams. See this. Just give for 5 minutes. Now see this minimum mode time diagram. It is very much similar to the bus minimum mode operation of that one. You see this. You see this general bus operation. You see this clock for read cycle for read operation. You know that. So at that T1 state, microprocessor these are in address. These are in address mode, but these address are in address lines. See this. These are address lines at T1 clock cycle. So a T2 clock, then another clock cycle are required to convert some address lines to the data lines. For that one, you want to give the address latch enable. These latches will convert these address lines to the data lines. For that purpose, it requires the one clock cycle, the time period, one clock time period. After that, remaining clock periods, so this address bus is converted to the data bus. So address bus is converted to the data bus. At the same time, some address bus is converted into the status also. Now because some the address lines are available like this: AD0 to the 15, A16 slash S3 to the A19 slash S7. So the S3 and S7 will represent the status lines. So whenever you want to convert some address to the data or address, it is enable, you can on the ALE. So the address is converted to the other state, that may be some data state as well as status state. So microprocessors want the data. That what read means here, memory to the CPU, memory to the CPU. So that purpose microprocessors perform the read operation. When it will be perform the read operation after the second clock cycle. After the second clock cycle. Why? Because T2 time period is required to convert address to the data. After the T3 onwards, address bus is completely convert into the database. So that's why RD bar is enabled, nothing but zero. It is zero because it is RD bar. Zero is on, one is off. RD bar. So why is DN is data enable? It is also zero. Why it is zero? Why it is enable? Why you are going to enable? So when microprocessors want to know that. So when you get the correct data or not. Okay, what is DT by R bar? You know that data transmit and the data receive. You receive the data, transmit the data by performing the read operation. You receive the data, so that's why it is zero. So DT by R. If it is one, data transmit nothing but the write operation. If it is zero, you can receive the data, that is zero. So I said that in the latches diagram and all, you know that IO by M bar, RD bar, DN bar. If it is 0, 0, 1, you see this diagram. You see this diagram. You see this diagram, decoder circuit, WR bar 0, 0, 1, 1, 1, 0, 0. You know that. You see this diagram. You remember this. If it is 0, 0, 1, you see this decoder. 3/8 decoder, IO, M by IO bar, then RD bar, then WR bar. You see this decoder, MIO bar, then MRD bar, MWR bar, okay, then IOWR bar, then IORD bar, and so you see this decoder circuit. If it is 0, 0, 1, what is 1, 0, 0, 1? IO read. If it is 0, 1, 0, IO write, input output write. If it is 1, 0, 1, memory read. 1, 1, 0, it is memory write. See this, or otherwise you can also see this. Okay, okay, you see this. It is zero, nothing but DN bar is zero, nothing but see this. So this will represent the entire for operation on this one. So at the same time, write cycle. For performing write operation, nothing but the CPU to the memory. Write operation means here CPU to the memory. Same. So this lines at T1 state, it has the address. So for converting address to the data, we are enabling the address latch enable. T2 clock cycle is required to address that one. So here this one up to this one, this diagram, you cannot confuse that one. This is the another state. So you can remember up to this one, T4 clock cycle. So then after enabling, T2 clock cycle is required to convert the address to the data buses. Then this is the data. This is the address is converted to the data for this. You know the TW is a wait period. So nothing but to connect this low memory device to the CPU. So you know that address is converted into the state, address is converted into the here the status lines, address is converted to the data lines. You know WR bar, because we are performing the write operation. When that perform the write operation after the nothing but T3 clock cycle. T3 clock cycle only. After the T3 clock cycle only, you are enabling that, but it is zero. It is also zero because microprocessors want to know whether we are sending the correct data or not. You know that what is DT by R bar means here 1 data transmission. That but DT by R bar is equal to 1. So here this one. This is the timing diagram of read cycle and write cycle. These are very much similar to the 100% similar to the general bus operation. This one is also there. So you know that microprocessor is fetching some information. So nothing but microprocessor is waiting that whether that entire mission cycle is completed or not, or entire instruction is completed or not. How to know that microprocessor that instruction is executed? How to know that microprocessor that instruction is executed? So for that purpose, microprocessor is generating these pins, hold and hold acknowledgement pins. But the same pins were also used to access the direct memory access and all. Okay, so this is the pin where hold and hold acknowledgement pins. Hold acknowledge means here the microprocessor is sending this pin to know that whether that instruction is executed or not. So if it is executed, then it will gives the hold acknowledgement pin can generate the hold acknowledgement. Okay, okay. Anyway, last then next class we will going to see the maximum mode of the application. Thank you.